Portland, Oregon. How's the audio? Okay, I'm going to be giving a short talk about the effects of a special kind of noise that often appears in occultation light curves, and that's temporally correlated noise. It's a bit of a mouthful. Next slide, please. Could I have the next slide? I'm the programmer behind IOTA. So I've involved myself for a long time in the problems associated with extracting so-called square wave occultation timings from light curves. These are occultations where the star can be treated as a point source and diffraction effects are simply too fast to be captured by cameras operating at 30 or 25 frames per second. I have to pay a lot of attention to the noise because it affects the math that you use for determining when you've achieved a best fit of a model light curve. I just threw up a quick example to kind of orient you to this. So if you were making a repeated measurement of a constant parameter, let's say baseline intensity, and the noise there has a Gaussian distribution, then you can get the best estimate of the baseline intensity simply by taking the mean value of the readings. But if the noise instead had a different distribution, say a log normal distribution, then you get the best estimate by taking the median of the readings. As it turns out, in spite of the fact that occultation light curve noise sources have a variety of distributions, they can be Poisson, Gaussian, log normal. In my experience to date, the net effect is always indistinguishable from Gaussian, and I've looked really hard for deviations from Gaussian. But the noise distribution, which is its histogram, is really only part of the story. The temporal characteristics of the noise must also be taken into consideration. Next slide, please. And that's what this talk is about. And the next slide shows graphically the effect to be discussed. So here we see three traces that are visually different, but they have exactly the same distribution histogram. They are all examples of Gaussian noise. They have the same standard deviation. What sets them apart are their temporal characteristics, which means the degree to which reading n reflects what has happened to prior readings. In statistics, one commonly encounters the term IID, which stands for independent and identically distributed. And many statistical analysis procedures require or simply assume the IID condition. And they do that because it enables them to make certain mathematical transformations without question. But it isn't always truly essential that your readings be IID for some of the procedures to still work. Now the top trace here does satisfy the IID condition. The other two traces do not. The observation values are identically distributed in all three traces, but the two bottom traces do not satisfy the independent condition. The noise at reading n depends on previous readings to some degree. Next slide, please. Now, the primary tool for detecting and measuring the temporal characteristics of noise is the autocorrelation function. What that function does is compare the noise with a copy that is shifted in time by one or more frame times and computes a correlation coefficient between the two at that time shift. The amount of the time shift is referred to as lag. At a lag of 0, the noise is being compared with itself, so the correlation coefficient is equal to unity. What is of more interest are the coefficients for the lag greater than 0. If you look at the right-hand plots, those are plotting the autocorrelation coefficients, and you can see at lag 0 it has a value of 1. But as you go to greater lags, depending on the temporal characteristics of the noise, you'll either have no significant correlation coefficients or you will see some. So these plots are excerpts from the noise analysis panel in IOTA. And the right-hand plot in each panel is a plot of the autocorrelation coefficients out to lag equal 20. At the top of each panel is a list of the ACF, that's short for autocorrelation coefficients, that meet a test for statistical significance. Those little dotted lines in the ACF plot are the limits of statistical significance. And you can see that in the bottom plot, RO discerned that there are 5 correlation coefficients that were statistically significant. But in the one up above, there weren't any, so there was no temporal correlation in that light curve. The power spectrum for pure Gaussian noise is theoretically flat, and that is shown in the upper curve. Whenever you've got, among other things, correlation effects going on, your Fourier power spectrum will no longer be flat. Next slide, please. It's worth spending a little time talking about what can cause the noise autocorrelation functions to have statistically significant coefficients for lags greater than 0. You know, I'll just read through the slide. This is probably the easiest thing. The most important one is the atmosphere boils and shifts. We just refer to that as scintillation. And this produces an intensity modulation of the incoming light that varies with time over some tens of milliseconds. So at our NTSC and PAL frame rates, we see atmospheric scintillation as time-correlated readings in light curves. But there are other things that can do it too. If the light curve slopes, so you were having some light clouds moving in, or if you're having, you know, the light is fading, you'll get a sloping light curve. Well, that makes point n depend a little bit on what happened at point n minus 1. So detrending is required to be able to depend on the ACF coefficients. Clouds can come by, and that'll put little blips and bumps, and that will again cause points to be correlated with each other. So you have to be able to normalize. So you really would like to have a reference star. But I can't stress the value of normalization. The reference star is such a valuable thing to have in your field of view. Something else that can crop up is just electrical noise. If you've got a little 60 cycle noise in your light curve, that'll show up. It makes point n depend a little bit on point n minus 1. But that can be Fourier filtered. Now, IOTA provides tools for dealing with all of these. Now, we're primarily interested in dealing with the effects of scintillation noise, so other observational conditions that can produce non-zero autocorrelation coefficients have to be dealt with first. Next slide, please. So here's the big problem, at least for me, dealing with extracting light curves and trying to say, this is what we know and this is how well we know it. Occultation observations are, by their very nature, one-off. You can't repeat an observation many times, so there's no direct way to study the statistical properties of our D and R time extractions. Now, the workaround that's commonly used is called Monte Carlo simulation. It proceeds by taking a noise-free model light curve with the D, R, B, and A parameters extracted from the original light curve, then adding realistic noise and refinding the D and R values. This procedure is then repeated thousands of times. The results are summarized in a histogram that shows how many times a particular solution occurred. Next slide, please. So this is from an IOTA error bar estimation panel. Well, the top plot shows the solution histogram when the observation noise has no temporal correlations. The autocorrelation coefficients at lag equal 1 and greater are effectively 0. The lower plot shows a solution histogram with the same amount of noise, same standard deviation, but with significant autocorrelation coefficients at lag equal 1 and higher. In this case, all the way out to lag equals 6, and those are shown at the on the bottom legend on the bottom plot. I should mention IOTA uses log likelihood for its best fit metric. Now, using this metric, the best fit is the set of parameters that maximize the likelihood calculation. And shortly, I'll discuss other commonly used metrics. Meanwhile, I just want to point out a few things on this slide. I'm showing some error bars. They're the vertical black lines. And in this particular case, I told IOTA to use as the confidence interval 68%, 95%, and 99.7%. Now, IOTA will let you pick what you want there. I plotted both of these using the same horizontal scale. I will point out that the vertical scale did change. If you notice, the lower one goes 0 to 2,000 in the histogram. The upper one is 0 to 4,000. If you were to visually overlay those two plots, you should shrink the bottom one by a factor of 2. The important message here is shown by the little green arrows. What you see is that the error bars for the same confidence interval widen as you have correlation effects added in your noise. In fact, for the 99.7 error bar, it's not even plotted on the bottom plot because I didn't use a big enough horizontal scale. Next slide, please. Now, we're more interested in, or used to measurements anyway, that have a Gaussian distribution of the solutions. That is just so obviously not the case for the distribution of occultation edge positions. You get this really sharp, pointy distribution that's quite unlike a Gaussian distribution. I don't want to labor the point too much or belabor it, but the blue curve on this plot is the best fit of a Gaussian distribution to the solution histogram of 100,000 Monte Carlo trials. Hopefully this also makes clear that for occultation edge position error bars, it would be extremely misleading to refer to them as 1 sigma, 2 sigma, or 3 sigma. Such terminology should be used only when the solution distribution is Gaussian, and that's not what we have. Next, please. I'm not quite sure why my foil comes through with some dark and some light, but let me just proceed. The standard metrics in common usage for curve fitting, like ordinary least squares, for example, assume that the noise is IID, independent and identically distributed. Now, you can just ignore that and go ahead. The solvers will still work, but there's a question posed by this slide, which is, will a fancier solver help? And I want to say, just to give a feel for why we think that a correlation-aware solver might be able to do a better job, and that's because it could make use of the extra information. It can compute the likelihood of measurement n given the value of measurement n-1. That's where the extra information would come about that might make your solutions better if you used a correlation-aware solver. But does it help? And I think I'm going to show that sometimes it does, sometimes it doesn't. Next slide, please. This is just to show you what a single Monte Carlo trial looks like. In this case, we're using a signal-to-noise ratio of 0.4. And the green bar shows, now there really should be dots, but it's fairly traditional and easier to see if you connect them with a straight line. And so the dark green line shows the model signal, And on top of that is imposed Gaussian noise with the desired temporal characteristics. Next slide, please. So I set up a series of Monte Carlo simulations that employed different solvers. Now, each one used a different calculation of the metric used to determine the best fit. The metric for an ordinary least squares solver, that's in the upper left-hand corner, is the usual sum of the squares of the deviations. This is a metric that is minimized to achieve the best fit. Now to the right is what you would call a weighted least squares solver. This one also sums the squares of the deviation, but weights each point by the noise level in that region. Again, this is a metric that is minimized to achieve the best fit. Now, IOTA uses a log likelihood solver, and it achieves best fit by maximizing this metric. And finally, at the lower right is what I'm calling a correlated log likelihood solver. And this includes a likelihood calculation based on conditional probability. That is, it calculates the likelihood of reading n conditioned by the value at reading n minus 1. This is the only correlated noise-aware solver in the experiment, and it only takes into account the autocorrelation coefficient at lag equal 1. Okay, so it's just an experiment to see if including some knowledge of correlation can result in a better solution distribution. Now, it's pretty hard to see much difference in these plots. It's easier to see the distribution differences if you look at the cumulative probability plots, and these are shown in the next slide. There's actually 4 cumulative distribution plots, and they just plot right on top of each other. I'm showing the error bars there at 95% confidence level. Now, clearly, there isn't much difference between the solvers here. They all produce essentially identical solution histograms, but it's likely that if a larger number of trials are employed, the agreement would even improve. I want to point out that the baseline noise sigma, well, that was the sigma b equal 5, is equal to the event noise sigma. That's also 5. I emphasize this because the situation when the baseline and event noise are not equal is rather different. Now I conclude from this plot that any of the solvers can be used when the noise at A is the same as the noise at B. The fact that the IID requirement is not satisfied has no effect on the solutions obtained. Next slide, please. Now, in the previous study, baseline and event noise were selected to be equal. However, it's often the case that there is a difference between baseline noise level and event noise level, as the bullet points on this slide explain. The reason that you get a difference in noise during the event versus noise during the baseline is that scintillation noise, which is usually the biggest noise in your signal, is proportional to the intensity. So if you've had an intensity change, in other words, if you've had a mag drop, you expect your noise to change as you go from baseline to the event. Your other noise would just be photon noise, the Poisson noise, which comes out as Gaussian, and that's also a function of intensity. And of course, we wouldn't be seeing an occultation if we didn't see a difference in the baseline intensity versus the event intensity. And what I've found is that when this is the case, the choice of solver becomes important, and we see this on the next slide. Now there are visually apparent differences in the solution distributions. The solver does matter. The correlated log likelihood solver, that's the one whose metric takes into account the value of frame n depends a little bit on what happened at the previous frame, is actually 3 times more likely to nail it. So that's the value of the peak at 0, not 0, 400. That's where I positioned the R edge. It's also a little less obvious that the distributions are narrower, but the cumulative probability plots are easier to use for such comparisons. Next slide. And now we can see that under some conditions, the choice of solver becomes an issue to be considered. The error bars that are shown here are at the 95% confidence level, and it's the same for all 4 solvers. Now the red arrow points out the error bars achieved with the correlation-aware solver. It has tighter error bars. The green arrow points out the error bars that if you just do a standard least squares based solver. And the brown arrow shows what RO does today. That solver doesn't pay attention at all to the temporal characteristics of the noise, but it does deal with asymmetric noise. Next, please. So I guess the question is, do we need a correlation-aware solver for occultation timing extraction? And I'm just going to read the slide. I'm not sure how well it shows up for you. Somehow we got black on black. The previous slide suggests that narrower solution histograms can result from a metric that takes into account temporal correlation. But the conditions were rather special. To see significant differences, a long duration, noisy observation with detectable noise asymmetry is required. In any case, none of the solvers introduced a bias. The most frequent solution, the peak of the histogram, is always where you expect it to be. It's where the model transition was placed. So at least in that sense, a correlation solver is not required. Slide, please. So I'm going to answer that question by saying the answer is clearly yes. You do have to take into account the temporal characteristics of the observation. And that's no matter what solver is in use. Error bars are always bigger when scintillation noise is present. It is essential to use correlated noise that matches the observation conditions when estimating error bars via Monte Carlo. If correlated noise effects are not taken into consideration, error bars that are too small, just too optimistic, will result. Now, whether or not the solver is correlation aware has a smaller effect on error bars and then only relatively rare conditions. The effect of using a solver that ignores correlation is to produce error bars that are a bit more pessimistic, which is probably not a bad thing provided they're not overly pessimistic. So at this point, until such time as cameras evolve to higher speeds and lower noise, RO will continue to use a non-correlation aware solver, given that the only penalty will be pessimistic error bars under some conditions. And that concludes my talk.